Okay, so we'll go over the introduction. We'll talk about the cluster computing architecture. Then we'll show some of the experimental results, and then we'll talk about the conclusion and the future work. So we'll start off with the introduction. So basically, modular robotics nowadays have been used in various platforms, ranging from agriculture, warehouse, uh, surgery, indoor mapping, military, automobile, space exploration, and even search and rescue operations. All this requires like smaller robots, multiple robots that can work together, collaborate, and then achieve some results. So what the traditional multi-robot architecture looks like, it has like various robots that collects the sensory information from the environment. For example, images, thermal information through infrared sensors, sound information, or whatever you call. All those information are mostly used to like understand the environment. So after the local data augmentation is performed, the whole collected data is sent to the cloud. The cloud performs all the major computations, including like finding any meaningful information from the collected data. If you want to perform any search and rescue operations, like analyzing all those heavy data and then pinpointing what are the focused areas of interest, all is done on the cloud. After all the information has been processed online, this is transferred back to the ground robots, where the ground robots can perform like the final end effectors. So what are the challenges with the existing architectures? So the main problem is that these robots has always need to be connected to the internet. If one of the connection fails, like they may become like clueless or what the next step should be. And the data might be mismatched or various kinds of problems might occur. So maintaining those infrastructure requires like a huge amount of cost. And also there is a high demand on the network bandwidth. If there is not enough network bandwidth, I mean, if you're collecting the data, it not may not be able to send to the cloud for faster processing. So there becomes a port problem. So what we did, we wanted to use whatever existing computations already the robots have. They can come together, collaborate, and then solve the important high processing tasks. So we used like the existing resources available within the cluster bots in the most optimized way. We came up with a one performance metric, which we'll talk about later. We denoted and did this as row, and then we'll compare our performance with the existing cloud architectures. And in this case, we have used like a lightweight Kubernetes. I'm sure you guys know about Kubernetes. So it's like a kind of, for example, you have like a software, you want to deploy it on a cloud. So what happens if like the cloud fails or something happens? You have to like maintain replicas of that software online. So instead of like creating like multiple copies, Kubernetes like it's like a resource management tool for the cloud that like creates replicas of the existing software. For example, if one of the instances goes down, it spawns up another instance, I mean, instantaneously, so that the enterprise like or a business can still stay if something happens. So we use that same concept in the edge instead of having it in the cloud. We did it on the edge robotics. So yeah, as I said before, model robotics can be various smaller modules. It can be various multiple robots that have like various sensors. It may look different and it may also look same. As shown in the figure here, like it can be similar to like the warehouse robots, and it can be different, like a drone or a ground rover that can be used in also in space explorations, even in the search and rescue and agriculture. And and this concept is called using the robot as a service instead of using cloud as a service, where the computation can be dynamically shared across various modules. So I'll talk about the architecture. So you have got, not sure if I can use this, but it's fine. The next few slides will show it. So it has got a server. For example, it manages all the resources, and then you have got all the slaves. So the master basically allocates all the tasks to that. So, but it's like a collective unit. For example, all the students are sitting here. You allocate like a captain. For example, Professor Padipta is like a captain. He can allocate tasks to all of you guys, but all of you guys work together in achieving the task. So it's basically the same thing. Whenever you deploy everything in the local architecture, in the local ground robot, so there's a central ground that you that can manually or automatically allocate as a master. So once that master is set, that master decides which bot can handle what kind of computations. So and it's a little optimized than the traditional Kubernetes. The traditional Kubernetes is mostly optimized for like x86 architecture that is more power hungry and more computationally expensive, like the computer. But the K3s is a little lightweight. It consumes even less than 1 GB of space, and it is mostly optimized for ARM-based operations, which is mostly the edge computation devices. Yeah, sure.
So we're talking about distributed system or like centralized control of the multi-node system.
It's kind of both. So you have got like various clusters. So these clusters will have like a central structure, and those clusters can come together and act as a single unit.
So there will be individually each robot will process on its board.
Yes.
And also it sends to the
Yes.
cloud
Yes.
architecture.
Yes. It's kind of hard, I do think. So yeah, so this. So as you can see,
Like when we're talking about load balancing, exactly what are we, I mean, what is the load here that we're trying to balance?
for example, I'll give you an example. For example, you want to do an object detection algorithm. So you take the image, but it takes a lot of processing to train the image and do the processing and find out what part of the image you're looking at, right? So that is like that is like a load,
So,
and that is like
computational.
yes. So and for this is like a master and this is like a slave, and these slaves can be further divided into various pods. And I gave you an example of like an enterprise software. For example, you have like a copy of it, and then you can create multiple copies of it. For example, if this is like a pod. So if there is a heavy traffic coming on, you can actually distribute the traffic into various pods. So if something goes down, the software still stays and it's not broken. The rest of the traffic can still hit the other pods. And this is like a performance metric we have come up. I mean, this paper is still under review and it has not come up on the IEEE Explorer yet. So once this is out, you can go through it and how we have derived this metrics. I can briefly go over the performance metric a little bit. So the performance is directly proportional to the network throughput. So it depends, for example, when I'd say like the master and the slave robots are connected, the communication mostly depends on how much network bandwidth is available. The more the bandwidth, the stronger will be the connection, faster will be the communication. Then the number of containers you have, the number of containers are basically the number of robots you have. More are the number of robots, the better be the performance. Then aim is like the max number of containers it can sustain. There's also a limit. If you go beyond a certain limit, the system will fail. So there is a limit to the maximum of robots you can have in a cluster. You can have multiple clusters, but in a single cluster, there is a limit to the number of pods you can have. It depends mostly on the RAM, the CPU, and other resources. If you increase the RAM, you can definitely increase the number of containers in a single cluster. And it's inversely proportional to the number of pods. And because more of the number of pods is basically like we are creating more and more replicas, and it's taking up more and more space in our system. And this is like the response time. So more is the response time you're getting, it's like you're getting a slower system. So it's like inversely proportional to the performance. So yeah, so this is the experimental setup we have used. We have used like 3 different Raspberry Pis. So we have chosen this as the master. This has got 8 GBs of RAM, and these are like the slaves. So all these are within the same network. We have used a ROSBot to, yeah.
For the performance, physically, what does it translate? Like, higher performance means what?
High performance means better than, I'd say, for example, how do you, so traditionally there was not a qualitative metric to measure the performance. This is like a qualitative analytical metric. You can talk like this laptop is faster than this, but is there any analytical metric to measure that? That metric is similar to that.
It's just like a combination of variables.
Yes, exactly. So we have quantified that, given it some values, so that we can actually compare with some existing resources. So we have used like a ROS bot that is like a turtle bot. You can have like ROS installed and perform some local tasks. So this is basically has like a camera attached. This goes around, performs a local path planning task, and at the same time detects the objects on its way. So what it does, it collects those images and then sends it to the local, the crossboard architecture we have set up. So what it does, it has got various pods. So these are like the replicas of the software. So whenever it sends like text like a picture, it sends it as an API to the one of the pods. These pods have like all the computations available. So these are all available all at the same time. So instead of like, so for example, if one of these gets overloaded or anything happens to this can come up and take up those positions. So if it takes like a large image and sends it to the one of the pods, and this gets busy in processing that image, but the bot is still moving and still taking up all, again, it's taking the images. So in the next image that it takes, it sends it to the next pod. And then by the time this pod, sends back the results, this is empty. And again, when it takes another image, it's basically like a cyclic scheduling, right? Like that happens in the OS. Like as soon as one of it gets free, it gets reallocated with another task. So there is always like available, there is always an availability for a new space and a new task, and the software is not clogged. You see what I'm saying? Any questions so far?
So when suppose one of the slave robot is busy like that, so the master robot can send information to any of the slave, and then like when the original slave which was busy earlier, when it gets free, so then the slaves can communicate among themselves,
No,
or they will
the
send
slaves cannot communicate within themselves. The slaves will only send it to the master. Master has like a dashboard. You can see like which pods are empty, which pods are free. Based on that availability, it can send a request to that. So whatever request comes to the master, then the master looks like which pods are available. Based on that, it decides. Yeah.
Hello, I have one question. So how do you load balance on the master? Because he has to arbitrate among all the requests. So it will be too much load for it.
It's just like a request. So each pod has like it's not, I'm just giving you an example, like if a pod and this pod is getting busy, can actually handle more than 1,000 requests. So it's and all the pods are like getting requests all at the same time. If one of the pod gets, for example, spawn like 1, 2, 3, 4, 5, 6 pods at the same time. If one of the pods gets busy, another pods gets deployed at the same time. So you have got 7 running pods, but one of the pods, since it's busy, you have got 6 pods available again.
No, my question is about the master. I mean, does he has to arbitrate all requests for designate pod, or the pods can take decision on their own?
The pods can take decision on their own.
I see.
Yes. Any other questions?
Fundamental question. When we're talking about a pod, I have a bit of a fundamental question here. So when we're talking about the pod is a like the processing power, we call processing unit, right?
Yes, yes. Virtual processing.
Virtual processing unit.
Yes.
And we can have robots with like different levels of this processing.
Mhm.
So that's why the robot one has only one, but
Yes,
robot two has two.
yes, yes. Yes, exactly.
So
And-
if they're processing unit, like you're saying, the pod can decide on its own, but someone has to decide, right? So how
Yeah,
to
I
make
have
a-
decided like for my basic software to run, I need this much amount of RAM, this much amount of GPU and all. So based on that, I created a pod. For example, this pod, for example, consider this slave. This slave doesn't even have that amount of computation power. So none of the pods will be created in this slave. Only the pods will be created on the master on the second slave. Get what I'm saying?
No.
For example, I need like 8 gigs of RAM to do some computation. So all the pods will be created on the master node. No pods will be created on the slaves.
Yeah.
So this is what the architecture is. And we have used like yellow V3 to perform the object detection. You must have known about yellow V3. And all these pods are like having all the software running using Docker as containers. You know about Docker and all? So it's like all the software dependency. It's like if you've used like Anaconda notebook and all, you have like different environment setup, all those package and everything. You need to run that software. You can like create like separate environments without affecting the other softwares. So it's Docker is similar to that. Whatever software dependencies you need, you can like have like a doc container. It's like a black box and you can deploy it as a single pod. So it does not have any, for example, you have any other software, any different kind of pod running, it won't interfere with the other kind of pods. It can run on its own independently. So yeah, and we have achieved like 5.94 seconds, and that is the average time to calculate the images sent from the Rosbot to the architecture to perform the object detection. And you have compared the results with traditional like cloud architectures. We have used like Amazon Web Services to measure those. We have used EC2 instances. We have deployed our system on T2 micro and T2 medium. As you can see, we actually received a timeout where one of the instances actually got clogged, and because since it does not have enough resources available. But in case of our instance, our scenario, if some timeout happened, it would directly spawn up another pod to take up its space since it's already getting used up. So we got a very high performance metric, almost twice the performance metric we got from the AWS architectures. It's like a traditional architecture where you have the computation uploaded to the cloud and cloud does all the processing and return it back. And our architecture actually got like twice the performance than traditional architectures. So yeah, this is actually a snapshot of the dashboard you have created. So it gives you all this temperatures, CPU temperatures, the CPU usage and other file system information. And in the future, what we want to do, we want to combine those like cloud architecture and the edge robotics to perform like a more variety of tasks. So there is still a lot of tasks that like uses even more computation that cannot even be handled by those edge robotics. But so those tasks has to be handled by the cloud. But but there is a problem of the cost and the network bandwidth. So we have to come up with like a trade-off, like which task should go on the edge and which task should go on the cloud. So it's like, so we want to implement like a reinforcement learning based technique to determine like which should go on the cloud and which should go on the edge. So that work is still in progress. So yeah, that is it for now. Yep.
So like there's one more, just like if suppose the entire thing is working in cloud and if the cloud fails, then entire system will fail, right? Like
It's the same thing. So what I will do, so since these are like physical pods, so one of the slaves will be replaced by like a cloud slave. It's like a virtual thing. These are like physical machines and the cloud will take up as a virtual machine thing. It will also have those pods. So if one of the pod fails, again, it will spawn up another cloud pod in that case.
So can you talk about the network? Like, what do you use? Is it wired, wireless?
We have you. I'm done. I've finished.
oh,
Yeah, yeah.
Yeah, about the network.
So let me say, all these are under the same VPC, the virtual private network. So all those bots, so this is like a cluster. And if you have like multiple robots, there will be a separate clusters, right? So if it needs to send an information, it can only send it to this private network only and not to any other cluster. And this is like an internet gateway. So you have like I'm not sure if I can see anything here. It's like a NUC. It's like a switch, an Ethernet switch. So I have used like the university LAN to provide the connection, and then it's like a gateway, like a router. And all those devices are connected to this router.
Are they all time synchronized?
Yes,
How do you do that?
we collect the timestamps.
Do you try to change the clocks to any master clocks?
Yes. At the start, every clock has been reset to the same. I mean T0, I'd say, so that any data mismatch has been taken care of.
Do you use like ETP or is just some simple?
Yeah, just some simple. We haven't had
Okay.
anything like that.
Hi, I had this question. So since you are talking about smart
Any other
robots,
questions? Any doubts?
yeah, hi,
Uh,
Santosh here.
small,
So,
when we transfer, when we transfer information, so there must be some information lost, like packets or something. So let's video, incorporate that in your performance metric.
Yes. So you mean like this is the thing that the network in bytes, the network out bytes.
We have an online question.